Hello students, welcome back to the next lecture on classical electrodynamics. And today we have lecture number 13. In the previous class, which is lecture number 12, we started with the objective of solving a problem in cylindrical geometry, namely that you have a metallic tube. So the metallic tube is divided into two halves, or it is cut into two halves, and the lower half of the metallic tube is maintained at zero electric potential, whereas the upper half of the cylindrical surface is maintained at some positive value, plus V naught. So the question is that we are interested to calculate the electric potential due to this kind of an arrangement at large distances away from the cylinder. So that means if you move far away from the cylinder, then what would be the electric potential somewhere there? And similarly, if you go into the interior of the cylinder, you can go in the interior of the cylinder wherein you are not touching the cylinder. Okay, that is what we mean to say interior. Anywhere in the inside of the cylinder, we also want to calculate what is the electric potential. So the configuration is a full circular cylinder. That means this particular upper half has to be kept on top of this so that it is a complete cylindrical tube. So there is a configuration. So this particular objective I already explained in the last class, but however, we have completed only the determination of the general solution to the Laplace equation in cylindrical geometry, wherein the z component, or that means the variable z is not required in our calculation. We say that a problem of this type is having cylindrical symmetry, and therefore what happens is we have solved the Laplace equation essentially in r comma theta, because z is not required, so only r comma theta, which is what we say the plane polar coordinates. So there is a considerable amount of work to be done, and that is why we cannot assume that it is too simple and leave it. Okay, so even though we say it is two-dimensional, the calculation is in polar coordinate, and in addition you need to know how we are going to apply the boundary condition. So we cannot consider that the problem is too simple that you don't want to solve it. It is not that simple, and therefore we have started in this way in the last class. So now I will go to the place where exactly we stopped in the last class, namely the general solution. So I think this is the expression that you have. Here it is. So you have the general solution. That means general solution in the sense that you are considering the linear combination of all possible situation corresponding to n equal to 1 and corresponding to n equal to 0 also. That is what I mean to say general. And in the last class we have seen the detail how we have rewritten the expression so that it looks somewhat like a Fourier series. So we have made considerable amount of adjustments in the constants in the last class, and then we are writing the expression so that it looks like this. So it looks like this means, what do you mean by that is that you already know how the Fourier series is going to look like, and this particular expression, if you see, it also looks like the Fourier series, and that is the reason why we have written down like this. And the only thing is that you have the two terms sitting here. One is r by a to the power n, and then a divided by r to the power n. As I already explained, either the blue color term or the green color term, any one of them will survive when we are going to discuss for the electric potential inside the cylinder. That means only blue will survive, and if it is for the outside the cylinder, only green color term will survive. So this is how the general solution looks like, and today or now we are interested to calculate what is the value for A0 and AN, BN, and then CN, DN. So it looks like many constants are there, but interestingly, if you see how many constants are there, if you see A0 is there, that is okay. AN is there, BN is there. So do you want to count that 1, 2, 3, 4, 5? Do you want to say that 5 constants are there? The answer is no. There are no 5 constants. At any given time, you will have to calculate only 3 constants. That means if you are going to find out the electric potential in the interior of the cylinder, then I need only AN and BN, and which means that I am going to demand, or I am going to put CN and DN to 0. So this has to, we are fixing Cn and Dn to be 0 so that you don't go to infinity. So essentially you will be calculating three constants A0, An and Bn. That is over. And then once you finish that, we will come back to the situation for the electric potential outside the cylinder. Now we need A naught. After that, we need Cn and Dn. So naturally, you'll ask the question. So ultimately, you are going to find two more constants, right? But the answer is no. We are not finding two more constants. That is where the interesting point comes. How we are not going to find is that if you are going to consider the boundary condition is given on the surface of the cylinder. So here A is the radius of the cylinder. Therefore, if I am going to substitute R equal to A, R equal to A is called the boundary. So if I am going to substitute R equal to A, this becomes 1. And at the same time, this also becomes 1. So both of them, when it is becoming 1, you can't do the summation 2 times, right? Now, how does this particular sum look like when it is 1? When you have 1 to the power n, here also 1 to the power n, it looks as if you are going to sum the series 2 times. And therefore, ultimately, what is the meaning is, the ultimate conclusion is the following, that whatever an that you are going to calculate, that value of the constant is identically same for the cn also. The value that you are going to calculate for the bn is also going to be the same for dn. So it doesn't matter whether it is an or cn or bn or dn. So these two are identically same. These two are identically same as far as you are going to put 1 here. Isn't it? So that means based on the boundary condition. And remember how we are going to determine the constants. These constants will be determined based on the boundary condition. Since the boundary condition will make this term 1 here, and the blue color and the green color infinite series are identical series. That is what you'll have to realize. Both the series are identical series, and therefore there is no distinction between an and cn at the boundary or on the boundary. So therefore, we are left out with the calculation of only 3 constants in our calculation. Therefore, let us proceed now. So let me therefore write down what is the required statement. But before that, let me first of all write down the given electric potential on the lower half of the cylinder and upper half of the cylinder. That part I will write down so that the English statement will be looking like an appropriate equation. Okay, this is the title that I would like to run. Yeah, here this is what I would like to say, that what is given is that you have the applied potential between 0 to pi is V naught, whereas 0 here in other case, that means pi to 2 pi. So this is how you write down the given statement. And once this is clear, we are interested to calculate the rest of the constants. So we have been using the symbol A for the radius of the cylinder, not capital R. So that is another point that you just note down. And once that is clear, we are interested to calculate the u of r comma theta for 2 cases, namely r much greater than A. Okay, it's much greater than, we will find out for greater than A, then much greater than can be done it. So I will make it just greater than, and then r less than A. So these are the 2 cases that we are trying to do. And let us first start with r greater than A case, and then you remember the appearance of the equation. So that's why I'm coming up, just to remember how it looks like, and I'm going to write down that now. So start from A naught by 2 and then rest of the things you write down. Every time I have to go up and see. Otherwise, if you have in the note, it will be nice. Otherwise, let me verify and write down. You have A by R to the power n into the rest of the thing is C and Dn are the constants, so easy to remember. And you have a Fourier series. Now it looks like a Fourier series clearly. You don't have two summation, right? Therefore, now we are going to apply the boundary condition. So the boundary condition is what is there. So let us therefore apply or we say using the boundary condition. So the boundary condition is in the top there. Therefore, I can use the Fourier coefficients formula. So only thing is that you should know now how to calculate the Fourier coefficients from the Fourier series. That is something required now. Then only you can evaluate. Probably I'll show for your reference. You already know how to evaluate the Fourier coefficients. That means A0 and then these two constants. This is a standard method. But in order to avoid moving on to another or searching for what is the formula, I'll show the formula corresponding to that for your reference, and then it will be comfortable. So here I am showing the definition of the Fourier series, and then this particular expression is what we are going to use it for the Fourier coefficients. So I am not going to explain this one. This is of course quite familiar to you. The only point is that you should remember that this is the expression we are going to use it for the calculation of A0 and AN and BN. Now here all the three are here combined with the 0 also. So you can see that n equal to 0. So if I substitute n equal to 0, you get A0. So that is how you get it here. And the rest of the thing, only thing is that we have 0 to 2 pi instead of minus L to plus L. So this is the first point, that you can always use it. But then you can ask the question how these formulas came. Okay, of course, this question you should have asked when you are learning the Fourier series. But now at least remember that how do you know, or what is the methodology of obtaining these expressions from this particular series? What is the technique? So the answer is that you will have to use the orthogonality property of the functions. What function is there here is sine function, cos function, and then 1. 1 comes when you substitute 0. What is cos 0? Cos 0 is 1, right? So 1 comma all these sine functions, that means sine x, sine 2x, etc. Then all cos functions, cos x, cos 2x, etc. That set of all functions is a complete set, forming the orthogonal set of polynomials. So that orthogonal, why do you want to use the word orthogonal, is because of the orthogonality property. So because of that property only, you have these two formulas for the Fourier coefficients. Just for information and for reference, I will also show you what do you mean by the orthogonality property or the conditions. These are of course very well known to you. Only thing is you should now be in a position to associate the terminology orthogonality property, and this is how it looks like. So that's all about it, and then let us now use this particular formula and then start evaluating the three integrals. So here we have let us first evaluate the A0. So A0 is originally given by 1 by pi, but I am putting 1 by 2 pi. Of course, let me finish this and then explain this u of a comma theta d theta, and that's all about it. So here the original formula will be having only 1 by pi, 2 will not be there. This 2 right now I am going to put, so that this 2 will, I am essentially putting this 2 here, so that I will be evaluating a0 by 2 itself. That is the idea. And then usually in the mathematics book it will be given as f of x into dx. So right now our function is u of a comma theta, but then this a being a constant, it is not a function of two variable. Remember, a is a constant and therefore it's a function of single variable. So a function of single variable means similar to f of x. So you have f of x dx. That's all about it. And now let us finish the evaluation of the integral, which is quite simple. And because the definition of the potential is split into two halves, the integral has to be split into two halves. That's what it is. Integral is from 0 to pi, where you maintain a positive potential, and pi to 2 pi, where you maintain zero potential. And that's all. So if you can evaluate this, we will have some expression like this. It comes to about v0 by 2. So actually this expression is for, I think it is for the a0 divided by 2. I have already brought this 2 here. So that point you remember. Already this 2 is transferred here. So that I want to avoid one more step there. Now once that is clear, we are ready to move ahead to calculation of the AN. Whether you call it AN or CN, whatever it is, I already explained you, right? CN or AN. Just for information, I said that both are same. So if you really want to write the same CN, it's okay. You see, A0 is there. After A0, what happens? CN is coming. So whether you write CN or AN, both are same, because the constant wise, if you see, it will be the same integration. So that is the reason why I started writing AN there. Okay. So now let us evaluate. The Cn expression is 1 over pi. Then the integral has to be split. Okay, splitting probably we'll do later. First we will write the general formula. And then you have an f of x. F of x is this dx. I think this has to be multiplied by the cos of n pi x by L. That is the formula that you have. Okay, f of x into cos of n pi x by L. That is how the integral looks like. And let us now split it into two integrals and evaluate. Since the integral is simple, I think there is no explanation. Let me therefore write down. So finally what happened is sine 0, sine n pi. That's how we get. Both of them are 0, right? So that's why entire thing goes to 0. So we have Cn is equal to 0. So the equation numbers are fine, right? So that is the previous one, equation 2, 3. Okay, now we are going to get some non-zero value for the dn. So because of the zero potential, what happens is, at least for that reason, some of the integral is simple. So we have to only evaluate the first integral. So the integral of the sine is minus, right? Minus cos. Okay, but I think that is not n pi. Okay, that should be n theta, right? Okay, so we will substitute the pi in the next step. So that's fine. But however, minus 1 to the power n can be simplified further. So minus 1 to the power n becomes minus 1 or 0, right? Therefore, you have an option of getting 2. So that's what I'm trying to write down, that there's an option of becoming 2 there. And this is clear. So minus 1 to the power n, if n equal to 2, what will happen? If n equal to 2, this becomes plus 1. So plus 1 minus 1, 0. So that's why 0 will happen whenever n takes even values. But if n takes odd value like 3, if there is a 3 here, then you get minus 1, so minus 2. Then already there is a minus, therefore this is plus 2 will become, and therefore you have two options where the odd and even numbers are going on. So ultimately what happened is, similar to equation number 3, you are also getting dn equal to 0 when n is taking the even values. So the entire Fourier series is going to survive only for odd values of n. So that is what is the conclusion. So let us therefore write down how the final expression looks like. So keeping this through 3 and then you have the 4 now. Let us substitute all these things. substitute all the constants into our potential, that is the general potential, namely equation number 1. Then let us see how it looks like. So I'll move on to the next side of the board. So now we can say that let us substitute this expression, then we will be getting the series will be looking like this. So now we are going to substitute the value 2v0 by n pi. So this is the place the constants are now entering into picture. That's all about it. And that's all about it. As I already explained, that you should have the two conditions. This is important. You don't have n equal to 1 to infinity. We used to write all the time, but now you see that 2, 4, 6, 8 we have to eliminate and write 1, 3, 5, 7 because n has to be odd. That is what we explicitly write down. And also this particular series is valid for r greater than a, which means that we have to use a by r. So the difference between r greater than a and r less than a is that this has to be inverted. So those things we have seen in the last class itself. One is the r to the power n series. The other one is the r to the power minus n series. So this is an r to the power minus n series. So that's all about it. But other than that, these constants will stay intact. And this looks nice. And this is the potential. We can say that this is the answer. But if you want to know the dominant term, now out of the infinite series, which term is dominant means naturally you can say that n equal to 1 term will be this much stronger one, because the infinite series will slowly, converging means what? The next terms will go to 0. So let us therefore evaluate only the first term, namely dominant term. So we can write like this. If you are going to have a single term like this, and that is how it looks like. As you can see, just n equal to 1 only you will have to consider here, and this n also you have to put a 1 here. So that will be the first term in the entire infinite series, that will be dominant. And of course v0 by 2 is anyway there. So you have this constant, and then you have a first term, second term, third term you are going to truncate. That means you are cutting it and throwing it, and therefore what happens is this equality is not possible, because you are going to truncate and throw all the terms after the second term onwards, and therefore equality is not possible. That is why I have written here an approximately equal to. Okay, and then plus you write down, you simplify this. This is the expression you write down here, and this is the expression which is valid for r much greater than a. So the difference between the previous expression and the present expression, these lines are not coming correctly. Okay, the difference is that this is valid for r much greater than a, and this is not exact, okay, but it is approximate. But even that approximation, see, when you're talking about approximation, it should be a good approximation. Okay, that is the point. So in order to make it good, what we have done is r greater than a has been rewritten as r much greater than a. So what do you mean by that is the next term, what will be the next term? You'll be having a by r square. So a by r square should approach 0. When it will happen? A by r square will approach 0 if this is 10,000 kilometer. If this r is 10,000 kilometer, then 1 divided by 10,000 kilometer whole square, that number will approach 0. It may not 0, but it is approaching 0, right? And therefore, in such situations, this kind of approximation is a good approximation. But if you are going to stay very near to the cylinder, just outside, then even though you write approximation, this will be a worst approximation. Okay, so therefore that point has to be noted down, that this is therefore true only for far away distances. That is what we mean to say double greater than here. So that is clear. And the second part, the last part I mean, is very simple, that instead of writing a by r, you have to write r divided by a. You are essentially inverting it. If you invert it, and that's all, as I already told you, that the constant, this constant, what is the constant? This particular constant is valid for both the Fourier series, whether it is r less than a or r greater than a. Just now I explained, right? So the constants are interestingly the same, and therefore our job is now easier, that you only invert this. That means r divided by a you write, and and you get the answer. So in that way, we can finish the work. Okay, so let us move on to the last case, but this being the main result. So the one which I am highlighting is always valid. It is exact result. Okay, whereas the one with a green color box, that is approximate result. So this is one part of the answer which is valid for outside the cylinder. Let us now therefore write down what will be the solution for inside the cylinder. So the rest of the thing is same. Now we'll have to write down only R divided by A. That's what I did. I said you have to invert this particular expression, and that's all. The remaining things, namely the constant, has to be maintained as original. So what was the constant? You have some 2 times V0 divided by n times pi, and then only the sine term survives in the series. And as usual, the rest of the thing you write down that it is valid for in the interior, and the dominant term can be determined if we are going to substitute n equal to 1. N equal to 1. Okay. And let us therefore substitute and see how it looks like. So that is to the power n. And this also sine n should not be there. N should be 1, right? Then sine of n theta again, so n equal to 1. So now it becomes approximately equal to, so you get V0 divided by 2 plus the rest of the things. 2 V0 and you have by A pi, right? That's okay. Then into r sine theta. And okay, so let me put a box to show that this is valid for at somewhere near to the axis of the cylinder. That's what it means to say. Generally, this approximation is valid only if it is good approximation, namely that you'll have to stay away from the boundary. So that is why the white color highlighted expression, that is this particular expression, is an accurate expression. That means exact expression because it has all the terms. Okay, so it is valid even if you are going to stay just near to the boundary also. But here you'll have to stay much away from the boundary. That means you'll have to go or approach the cylinder. You'll have to approach the cylinder axis so that this approximation will be valid. So that's the difference between these two. But the highlighted one is a exact representation or the solution. So that is how we get the solution. And in principle, we got the answer. You got the answer for both inside the cylinder and the outside the cylinder. So probably, so that's fine. So that was our aim actually. So so you'll have to now recognize and recall what happened in the yesterday's class and today's class. So we actually started yesterday's class beginning, that is the starting point, and now we have completed it. Okay, so the entire step you'll have to combine and then realize what are the steps involved. So it is not that the mathematics is not the one that you'll have to worry about, but you'll have to remember what are the steps, what we are doing. That is how you'll have to identify what are the things that we are doing in order to move further. So a similar kind of job has to be done when you are involving 3-dimensional situation. So as I already told you, when in the case of 3-dimensional situation, you will be getting the Bessel functions, and therefore orthogonality property of the Bessel functions are required if you want to determine the constants. Okay, that is where the next level complications will come. So your knowledge about the Bessel functions has to be therefore emphasized, and after that the other things will be reasonably simple. You can do it. So I will stop here. So because this is the solution that you got it, probably I would like to do something on what are the boundary conditions to be satisfied by the electric field in dielectric medium. We also started a topic on the dielectrics. Okay, so in the next class, I would like to discuss how to write the Maxwell's equation in presence of the material medium, And we will also discuss what are the boundary conditions to be satisfied at the interface of two dielectric medium. So because I already said that we will discuss on that. Essentially, I think 1 or 2 lectures before we already discussed on the dielectric polarization, and we also calculated what is the electric potential due to a dielectric medium that got polarized. So in continuation to that, we would like to know, suppose if you have two dielectrics, okay, and if an electric field is there in that region, then how the dielectric will affect, because you are going to have two dielectrics, right? So how the dielectric is going to affect the electric field inside. So that we will see in the next class.